Are you going to be timekeeping, Jeff? Yeah. Okay. That's awesome. All right, everyone. My name is Joao Bento. I'm a postdoc at ANU, and I'm the Australian Node Manager for the HAT South project, which means I'm charged with the task of giving you the obligatory HAT South talk that happens every year. So for those of you who don't know what HAT South is, I'll give you a very brief introduction because there's too much to say in 10 minutes. And for those of you who do know what HAT South is and are slightly getting bored of hearing about HAT South, remember that if you are bored about a project and it keeps coming up all the time, it's probably not entirely rubbish. And obviously this is not just my work, it's the work of a large group of people, as you can see, and these are probably the names of the people who've made most of the contributions and actually have some active work on HAT South at all times. And as you can see, it's also a collaboration between several universities. I've highlighted basically Princeton, which is where you can think of the headquarters of this project are, and ANU, Max Planck Institute in Germany, and the Pontificia Universidad in Chile, who basically manage the three nodes in some way. And then these are just the current locations of people, and they keep going around to all sorts of places. So I'll just briefly talk a little bit about the project itself and motivation. I'll talk about the survey, including some of the previous and future aspects of it. I'll just highlight some of the results because there's way too many things to talk about, and I'll talk a little bit about the future as well. So the idea of HAT South is that it is the largest ground-based transiting exoplanet survey in existence, largest in terms of number of telescopes. And it was originally designed to be a follow-up to the HATNet project. So it builds on the experience from the HATNet and obviously applies it to the Southern Hemisphere. And it's aiming to find hot Jupiters, Neptunes, and potentially super Earths around mostly K and early M dwarfs. So it observes in the R band, which means it's optimized and slightly biased towards later stars. If you actually look at the distribution of stellar types, it's found stuff around. It's not just those, but it is most of the sort of the late K and early M planets are actually starting to trickle down now. And it is actually aimed to find to explore a parameter space where it's got a slightly longer period than what most other ground-based surveys have done, and I'll talk a little bit about that. And one of the things I want to say is that it's actually fully automated. So most of the names of the people that I showed in the beginning spend most of their time on the follow-up, as in sort of confirmation and characterization of planets rather than necessarily on the telescopes that actually do the observing and find planets. And obviously the idea is that all of these targets are still bright enough for a follow-up of atmospheric compositions. And one of the points that I've been asked to make is that there's actually quite a lot of science in the light curves that come from this project, and we're understaffed when it comes down to doing lots of interesting science with it. So if you like non-planetary related things that photometry can give you, give it a shot. And so, as I said, so it builds on the experience from the HATNet project, which had single telescopes on single domes, and there's 5 of them in the US and a couple of others in Mauna Kea, and basically applies that to the Southern Hemisphere, right? And using the principle of more is more. You put more telescopes in the same dome and you just get more of the sky, right? And so you can think of HATNet as sort of HAT North, where most of the hard work and the initial characterization was actually done. And then HAT South includes 3 locations. So at Las Campanas, at the Hess site, and obviously this is the one I'm in charge of in some way at Siding Spring. And the idea here is if you put them sufficiently far away in longitude, you can monitor the same field for almost 24 hours a day using obviously different telescopes. And it's nighttime in one of these sites at all times. So you could actually get, in principle, 24-hour coverage provided the weather cooperates. And we've had a series of several weeks where we actually have continuous coverage of all of these things. And so what kind of data do you get? Well, depending on what you're looking for, you get variability in stars and etc. But the thing we're really interested in is the planets. So once you face fold the light curve, you get something like that where you clearly see a transit. So if this is a short period planet, you get lots of dots. If it's a long period planet, you get a tiny little transit in the middle when you actually face fold it. But mostly the data are good enough for that sort of thing. And the objective is to do sub% precision on most of the stars that we care about. And as you can see, actually our range includes R from 11 down to almost 14, in which we can do actually sub% precision. And that's really important for us to find all the planets and the hot Jupiters and Neptunes that we care about. And so most of the results so far, so this thing has been running for 7 years, gathering data automatically, mostly runs by itself without much human interaction. And we have currently 36 planets published, 12 submitted or awaiting acceptance, and some of them are already on AstroPH, some will be coming out soon. And we have another 14 confirmed that are whose papers are either being prepared or they've been confirmed as planets, and some more characterization observations are still needed. So those will be coming out soon. If you're interested in them, you can go to headsouth.org/planets, but obviously all the confirmed ones are also on the Exoplanet archive. So you can find out all the papers and information about it. Right? And there's been a few other papers, such as Dan Bayliss' paper in 2017 that actually sort of announces one of the other planets, and then we've included some follow-ups from Kepler systems where we've actually identified them as being binaries instead. But there's also all sorts of other things that the team is involved in and has been done. So just a couple of highlights. So the question I'm usually asked is, have you found any super Earths? The answer is no. But we have found some Neptune-sized planets. So HATS 7b and 8b are both sort of Neptune mass planets. As you can see, these are the discovery light curves and radial velocity for HATS 7, I believe. And wow, that has not worked out. There we go. And this is an old plot, but actually shows where the position in a radius mass diagram is for HATS 7 and 8b. And as you can see, at the time of discovery, most of the rest of the planet is populated by Kepler planets. So we were really at the time competing with this sort of parameter space. This has been filled up a little bit more since. Then there's HATS 17b, which was at the time the longest period transiting planet found from the ground. And this really shows the strength of the project in that sense. So the longitudinal coverage allows you to actually find this sort of thing. I say at the time because annoyingly there's this TRAPPIST-1 system that happens to have an 18-day period planet, which is scooped as far as the transiting planets from the ground period comes through. But there's a couple of other 20-day period planets that we've got waiting confirmation on the pipeline. And this is also an interesting point, so I don't have a lot of time to talk about this, but essentially on the complete other end of the period scale, we found something orbiting in less than a day, which is not necessarily uncommon, but the actual host star shows some variability on the 10-day period timescale. So its rotation, this planet orbits more than 10 times around the star at the same time that the star does a full rotation. And when you actually model how that's going to, or how the tidal interactions are going to actually affect the star itself, just about any scenario that you can put in leads you to a situation where the planet's actually going to spin up the rotation of the star. So if you're interested in this a little bit more, check out Nav et al. 2016 for more details on the paper itself. And this is just some highlights of something that's coming up soon. So I'm hoping to submit this paper either tomorrow or the next day. And it should be another 4 sort of super Jupiter style planets. And the interesting thing about these is that they're all orbiting F-type stars, and they're all in very similar or relatively similar conditions. So the periods are relatively similar. The stellar types are all similar temperatures. The actual equilibrium temperature of the planet is also on a range that spans only 500 Kelvin. But the actual planets themselves, even though they're roughly the same radius, they actually spend the entire mass to get something that's sub-Jupiter all the way to something that's almost 10 times the mass of Jupiter. So this tells us a little bit that the evolution of these planets, even though they end up in relatively similar conditions, obviously the actual host stars and the composition of the clouds they form from has a huge impact. Right? And actually, HATS 41 host itself is actually particularly interesting. This is the almost 10 Jupiter mass planet. It is actually something that we noticed recently. It is the highest metallicity star to host a transiting exoplanet ever found to date. And there's a few considerations on the paper coming up soon about how that fits into a context. And people have speculated that there might be 2 different classes of exoplanets where you have sort of the low mass exoplanets forming in some way with some metallicity dependence. And when you actually get above 4 Jupiter masses, it sort of becomes a bit less dependent on metallicity. But I think, as you can see here, this part does not have any transiting planets. So it's quite possible that the sort of the closer in systems are still metallicity dependent. But more of that on the paper, or come and talk to me if you're interested. And so, quick summary, because I'm running out of time. Hot Jupiters and Neptunes are still cool. Well, they're not. They're still hot, but you know what I mean, right? They're still interesting, and I think that if I got anything out of the conference so far is that actually life is really hard to find and mostly really boring, and Earths are boring. So keep looking at hot Jupiters and Neptunes, because these are the rare ones. Even though we know a lot about them, the one thing we do know is that they're rare and interesting to extreme in some way. And so the HAT South and HAT NETS in this case are still going strong for a few years, and they're providing you with lots of planets you can actually find stuff about. And the plan is, once TESS goes up, the idea of all of these as planet discovery things goes out the door because it becomes obsolete. TESS will do much better, but TESS will cover a shorter baseline of up to 27 days for most of the sky. And what we can do is we can keep observing TESS fields and look for signatures and try and actually confirm and even potentially detect planets on longer orbits. And I've put this up here because that's been brought up. It's unlikely that we'll be able to find any exomoons with this, but if they're obvious, they'll be there. And how much time do I have? 30 seconds? Okay, so I'll just talk about HAT Pi, which is not necessarily a completely new idea, but again, on the principle of more is more. It would be great if we could monitor the sky, the entire sky, at all times, or at least something close to it.
Why isn't it HAT 2 Pi?
Oh, this is a good point. It should be something like that. Maybe that's just too long. But it is not necessarily a new idea, and I should point out that there's another project called EveryScope, which is already in place and observing, which focuses on the same idea. But this is a project that will include 63 CCDs mounted on the same mount as you can see here, and taking images on a 30-second cadence. The idea is that this thing just moves on RA, and as soon as it runs out of range, it comes back and keeps monitoring the sky like that. So we should have a lot of the sky in the same way. And this is already in place, mounted in Las Campanas Observatory, right next to where the HAT South thing is, and we'll start observe soon. So if you're interested in 30-second cadence of quite a lot of the sky, you can do transients, exoplanets, asteroids, all sorts of new things that we might find. So come and talk to me about that too. Thanks.